Okay, we're going to have some more fun now. We'll see if this fun lasts longer or shorter than 1 hour, just like 1.3. I've glanced at these, decided they were interesting enough to do, but I have not solved them. So again, this might be a good opportunity to show some problem solving strategies that I myself use. We're going to start with number 211. It should be pretty straightforward and should be a review. So if we look at 211, it's just evaluating this integral. Integral from 0 to pi of sine minus cosine. So hopefully you have your table of integrals, or you can use what you know about derivatives. To take the antiderivatives of sine, you just ask yourself, the derivative of what equals sine of x? And then we do the same thing for cosine. And we get that the answer is negative cosine of x. The antiderivative of sine is negative cosine, and similarly, the antiderivative of cosine is positive sine. We evaluate that at pi and 0 and take the subtraction, take the difference. We're going to get negative cosine of pi minus sine of pi minus, making sure to include parentheses, negative cosine of 0 minus sine of 0. Think about the unit circle again. We have pi and 0. Cosine is going to be the x-coordinate. Sine is going to be the y-coordinate. But pi, the x-coordinate's negative 1. So we have negative 1, positive 1. Sine is the y-coordinate, which is 0. At 0, the x-coordinate is 1. So we have negative 1 minus the y-coordinate, which is again still 0. And we're going to get 1 plus 1. 2. All right. And in fact, if we did a little horizontal translation of this, a little shift, if we shifted this over pi over 2, we could have used the formula for even functions. But that's not what's going on here. That's how we do it, and that's what it looks like. Let me know if you have questions on that one. And then we really get into the example application problems with 215. Some of these are pretty straightforward. Some of these are pretty wacky. Tried to get a little mixture of both. Let's see what we have. 215 says that we have a regular n-gon, which is just an n-sided polygon with sides of equal length s, maybe like a regular pentagon, a regular hexagon. And this n-gon has perimeter n times s, right? So again, just looking at this, if each side length is s, what's the perimeter? 3s. If each side length has s, what's the perimeter? 5s. That's all it's telling us here. Sometimes in problems like this, if there's too much going on, it's just like, what is it talking about? Just draw some examples, and it can usually help a lot. So perimeter in general is just how many sides are there times what is the side length. Write an integral that expresses the increase in perimeter. So we want to know how the perimeter increases. We want to know the net change of the perimeter. What net change of P when the length of each side increases from 1 unit to 2 units, and evaluate the integral. S increases from 1 to 2. So we're going to need to think about this as a function. So in reality, this is a function of 2 variables. How many sides are there? And how long are the sides? But in this problem, it's saying, let's just look at a single n-gon. I don't know how many sides it has. I can't draw this. I don't know how many sides it has, but its perimeter is just going to be n times s. We can think about that as a function. Perimeter function is a function of s for a single n-gon. Assume n is fixed. Assume n isn't changing here. There are other ways of approaching this problem, but that's what this book is asking you to do. Well, the net change of this function, by the net change theorem, the net change when the side is 2 between when the side is 2 and the side is 1 is the integral from 1 to 2 of p prime of s. That's exactly what the net change theorem says. Okay. Now, of course, you could also just calculate this directly. Actually, oh, it wants you to set up the integral. So no, you can't. It wants you to set up the integral and evaluate the integral. But again, we know what the answer is going to be. It's going to be 2n minus 1n. It's just going to be n because we already have this formula. This is just giving us practice using the formula and seeing where the integral happens to be. So we know that p prime of s, I won't write it here, but we know that p prime of s is the derivative of this with respect to s, thinking of n as a constant. So think of this as 2x, or 3x, or 5x. It's n times our variable. So its derivative is just going to be n. Now the integral, the antiderivative of a constant, is a constant times s. And of course, you're probably losing your mind right now. You're going, Jason, we're going in circles. We are going in circles. We had to find the derivative, and then we calculated the antiderivative. And remember, that's the relationship between derivatives and antiderivatives, right? Mostly the relationship. Remember, there are infinitely many antiderivatives. But for a definite integral, we can choose whichever antiderivative we want. Usually we choose the one that has c equaling 0. And then, of course, we plug in 2 for s. Sometimes you'll see this notation down here. Sometimes you'll see this notation that just reminds you what your variable is. Just like if you remember, we could also add something like this. We usually used i's, but it didn't have to be I. This just tells you what your variable is. It's the same idea. So sometimes you might see the s equals here. You don't have to write s equals, but sometimes it's helpful because it's not clear what our variable is here. Sometimes it is clear. And then when s is equal to 2, we're going to get 2n. When s is equal to 1, we get 1n. And again, you can be frustrated. We're going in circles. That's fine. This is just practice. Yes, we we just went in a big loop and we're back to where we started, but it is just practice. And the perimeter increases by 1. Sorry, by 1n. If we increase the side length from 1 to 2 for an n-gon, the perimeter increases by n. And in fact, you could get the same thing. That if the perimeter increases from 2 to 3, then you get the same change. And you could take this to a couple other places, but that's all this problem wants you to do. All right, so that's 215. A little silly, but some good practice. Don't worry, things will get harder. Do 223. Suppose that a particle moves along a straight line with this velocity, similar to what we did in the lecture problems. And our velocity here is v of t equals 4 minus 2t. And t is in the interval from 0 to 2. Remember that this notation is the same as what the book writes down, that t is between 0 and 2. And we're in meters per second for this velocity equation. Find the displacement at time t and the total distance traveled up to t equals 2. So there's really two parts. The displacement at time t and the total distance traveled in the interval. So the displacement, remember, is just the integral of the velocity, whereas the distance traveled is the integral of the absolute value. Now here's where you have to be really careful with your variables. So the displacement at 2, between 0 and 2, would be the integral from 0 to 2. But we want the displacement at time t, so it's going to be the integral from 0 to t. But this is incorrect, what I'm writing down. It's the integral of the velocity, but we have one variable that's meaning two different things right here. You cannot have a t up here and a t in here. I realize that all of you could do this and get the right answer, but it's mathematically false. It is a lie. Okay. So we're going to choose a different variable here. Any variable works except t. S is the most common, I would say, in this situation. You could use x. X is the most comfortable probably, but that's how you're going to have to set it up. A variable in your limits of integration cannot be the same as your variable in the integrand. And that especially pops up when we use the first part of the fundamental theorem of calculus. If we took d dt here and we had t's inside, that looks super weird. All right. So that's what we get here. Take the antiderivative with respect to s. We're going to get 4s minus s squared. We're evaluating between s equals 0 and t. Again, this part is optional, but recommended when you have multiple letters. So here, when s is 0, we're just going to get a bit. Oh, so let's start with the upper limit. When s is t, we get 4t minus t squared. When s is 0, we're going to get 0 minus 0. We do get 4t minus t squared. And I realize that you might be frustrated because if you just had this in t's to begin with, then you wouldn't have to do that extra step, but it's an important step. And I want to take 30 seconds, 60 seconds to make a very important comment. In situations like this, that distinction seems silly. It seems pedantic. But the reason why it's important, the reason why I'm forcing it to be this way is because in some situations, the more complicated the problems or the further you go in mathematics, that thing can cause a mistake. Okay? When we get into specific types of problems, we need to be very exact about what we mean. And we need to be precise because two things can look similar, but actually mean completely different things. So that's why we're harping on it. Yes, in this problem, you can still get to the right answer, but mathematically for proofwriting and stuff like that, like someone else needs to know what you're talking about. And so the clearer we can be on that, the better. And that's really why I care about it a lot. So at any point t, this is going to be the displacement. Where t, again, any point t being from 0 to 2. That's our displacement. Distance traveled is a different story. Distance traveled over that interval is going to be the integral from 0 to 2 of the absolute value of the velocity. And just like before, we need to split this up into two parts. You could do that and get some practice. Another fun way of doing this, which is just an opportunity to see things from a different point of view, right? Is we're looking at the function 4 minus 2t. So when t is 0, we're at 4 up here. And when t is equal to 2, we're at 0. So actually, the distance traveled on this interval is equal to the displacement on this interval because we're never moving backwards. Our velocity is always positive or 0 on this interval. In this case, this function's positive on the whole interval, and actually, we just get that this is equal to the integral from 0 to 2 of 4 minus 2t dt, which actually we already calculated to be that. But we can do things in all the steps to make sure we don't make mistakes. Now we're going to get 8 minus 4 minus 0, or just 4. Our units are going to be meters. Total distance traveled between 0 and 2 seconds is 4 meters. Normally, to deal with the absolute value for a continuous function, if the inside of the absolute value is continuous, you would just set it equal to 0, Find where it's positive, where it's negative, kind of like that first derivative test from last quarter that we also covered in the earlier videos. That was done in 1.4.2. You want to see that again. All right, 231 is next. I have to make sure I've skipped problems before and ended early before. Try not to do that. Water flows into a conical tank. Okay, everyone loves that. Does it say whether the tank is conical upward or downwards? Which way is the cone oriented? Let's just guess, and then we'll see if it's a problem later. We have a conical tank. Let's say it looks like this, with cross-sectional area pi x squared at height x. That's where it tells us. It's telling us this area here is a function of x, and the area is pi times x squared, where x is the height, it says. Wait a minute. Is the tank sideways? Or is the height the same as the radius? Because in general, the area is going to be area of a circle. So pi times the radius squared. So it looks like the height is actually the same as the radius at any given moment. That's good to know. So write that down. Height equals radius with this cone. Any cone will have a relationship between height and radius. This one looks like it's equal. Let's just make a little note. Keep that in our mind and keep reading the problem. And volume, okay, so this cross-sectional volume now is going to be pi x cubed over 3. All right, that's where it tells us. The volume is also a function of x, and it's pi x cubed over 3. In general, the volume of a cone is pi times the radius squared times h over 3. So if h is equal to x, that becomes the same thing. So yep, height is the radius for our special cone here. If water is flowing into the tank at a rate of 1 meters cubed per minute, the water is flowing into the tank at a rate of 1 meter cubed per minute. Glug, glug, glug. I can't get a good picture for this, but imagine water going in there. Find the height of the water in the tank after 5 minutes. What's the height? It's x. Find x after 5 minutes. And then find the change in height between 5 and 10 minutes. Height between 5 and 10 minutes. So, right off the bat, it's not immediately clear what this problem is doing in this section, but we'll get there, okay? So the first thing is, okay, what is the height after 5 minutes? So we know that the volume, I don't think the area, I think this area is mostly just telling us that the height is equal to the radius. I think that's probably most of its use. Again, showing these problem-solving methods that I use on first working through these problems. Okay, so what we're going to use is this volume equation, okay? Because we know that the volume equation is related to its height, and that's going to be pi x cubed over 3. And we want, what is the volume after 5 minutes? Let's write x star, where x star is height after 5 minutes. So we need a relationship between the height and time. Okay, and that's where things, I believe, are getting tricky. And that's where we're going. And that's why we want to use the volume, because we know the rate at which the volume is increasing. Right? We know that the rate of change of volume with respect to time is +1. Assuming that that x is in meters, right? It doesn't specify that x is in meters. I guess x can be in whatever unit we want it to be. Say x is in meters. So what does this remind you of? Implicit differentiation, related rates. Okay, and I don't know if the book is going for something different, but this is the only thing that I can see. The only approach that I can see. So what is the rate of change of volume with respect to t? Well, we just ddt both sides. And when we ddt both sides, what are we going to get? We're going to get the left-hand side is dv dt. And the right-hand side, implicit differentiation, the 3 comes down and cancels. 3 pi x squared over 3. But because we're taking the derivative with respect to time, not x, chain rule says dx dt comes right here. All right, let's see where this takes us, because I've got no clue. I've got no clue right here. And then we know dv dt is 1. And what we're curious about is, what is the height after? We need the height after 5 minutes, or we need the volume after 5 minutes. We really want the volume after 5 minutes. No, we do need the height after 5 minutes. Why did I write this? We just want x star. We're using the volume to help us get it. Okay. All right, this would be a really good example for asking for clarification. I guess it's kind of implied by the wording, but yeah, it wants us to assume that the tank is empty at the start. Okay. If the tank is empty at the start, right, then the volume is 0 at t equals 0, and the volume is going to be 1 meters cubed after a minute. And then we can use this to find a relationship right here, and so on, right? It's going to be 2 after 2 minutes, and so on. So the question is, what is the height after 5 minutes? Well, after 5 minutes, the volume is going to be 5. And we know that the volume is going to be pi x cubed over 3. So we just solve for x. We solve for x, we're going to get 15 divided by pi equals x cubed, where x is the cubed root of 15 over pi, which is approximately cubed root 15 over pi. Cubed root's the same as an exponent of 1/3, about 1.684 meters high after that. Okay, so that's the answer to part A. Now there's a couple of ways of doing part B. Find the net change in the height. Now one of them, we could just find the height at 10 minutes using the same exact thing and take the difference, or we could have some fun and use the net change theorem using what we did over here. We found the relationship between the rate of change of the volume and the rate of change of the height over time. And if we solve for that rate of change of height over time, we know the net change of height, the height between 10 minutes and the height at 5 minutes, by the net change theorem, is the integral from 5 to 10 of the derivative of x with respect to t dt. The derivative of that height function, the rate of change of this height function. Now there's a bunch of different formulas, there's a bunch of different variables. That's why I'm writing it like this, but you could use the Newton's notation x prime of t as well. right? If you wanted to. It looks a little weird because usually x is our independent variable, not the dependent variable, but this works as well. And we're going to get, this is the integral from 5 to 10 of the derivative, which is 1 over pi x squared. Write that as 1 over pi x to the negative 2. Oh, wait. No, that's the problem with doing this. This is a function of x, not a function of t. So fundamental theorem is not going to work in this format unless we actually knew what x was in terms of t, which we could by using this, right? In fact, we generalize this, because I still want to show this net change theorem usage. The volume is really just t. The volume is just however many minutes we go by. So the t is equal to pi times x cubed over 3. Multiply both sides by 3, divide by pi, and take the cubed root. And again, when t is 5, that's where we plug in 5. We get our answer that we found before. And then, so this is x of t. And you can take the derivative of this. With respect to t, you could actually use this formula and plug in the x as well. A couple of other ways of doing this. But again, we do know at the end of the day that it's just going to be x of 10 minus x of t. Now we'll get the cubed root of 30 over pi minus the cubed root of 15 over pi. And we'll get that this net change approximately equal to whatever that is. This with a 30 minus that with a 15. We'll get the net change of 0.438 meters between those two. And again, if we just think about it, what do we think should happen to this rate of change? Or how does the net change? How is the radius and the height changing over time? It should be slowing down. So the net change in these 5 minutes should be bigger than the net change in the next 5 minutes. Because the volume is like the trickle, the flow is constant. And the bigger the tank gets, the longer it's going to take for it to increase because it's so wide at that point. And then, so that's the net change. This over here was the height. They're both in units of meters. You can check your answers over here. That's exactly what we typed. The net change, yep, that's exactly what we typed as well. Because this is an application, I will prefer decimal approximations. Otherwise, I prefer exact answers like they have here. Okay, next problem. Which one was that? That was 231. So the next one is going to be 233. And then we'll do one more after that. The following table lists the electrical power in gigawatts, the rate at which energy is consumed. So we're looking at a table of rates, kind of like we did at the beginning of chapter 1, used in some city for different hours of the day in a 24-hour period. So 13 will be 1 p.m. With hour 1, because corresponding to midnight to 1. Oh, maybe I lied. Hour 1 is the first hour, which is midnight to 1 a.m. So hour 1 ends at 1 a.m. Hour 13 will end at 1 p.m. So this is like the 24-hour clock when that hour period ends. Find the total amount of energy in gigawatts consumed in a typical 24-hour period. So again, this is really not really a 1.4 problem. Just add it all up. Now, if there were formulas and stuff, we could use some fancy summation notation. But remember, net change. This is really what it wants you to tie into, just like we did in 1.1. Net change is just the area under the curve of the slope function. This is telling us the slope. Well, if we're using 28 gigawatts, the rate at which wait, gigawatts is a rate? I thought gigawatts was a Wait, the units. Okay, gigawatt is a rate. That's, yeah, that. I think I'm getting confused by Back to the Future right now. Gigawatts is a rate. So the total is going to be gigawatt hours. Okay, great. Definitely not 100% on all my units for everything. Good thing the problem helps us out. So yeah, you're just going to be adding these all together because in the first hour, we're using 28 gigawatt hours every hour. So in that first hour, we're going to use 28 of them. In the next hour, we're also going to use 1 hour's worth of 25 and then 24. So really just adding this all up like so. So can do it a variety of different ways. If I were doing this myself, I'd probably copy and paste it into a spreadsheet and then just add it all up from the spreadsheet. Or could go up and add it all manually. A couple of ways of doing this. See how good your 10 key skills are if you have a 10 key, but yeah, it's 28 plus 25 plus 24 plus 23 plus 24 plus 27 plus 29 plus 32 plus 34 plus 39 plus 42 plus 46 plus 48 plus 49 plus 49 plus 50 plus 50 plus 50 plus 46 plus 43 plus 42 plus 40 plus 37 plus 34. And you get 911, which is hopefully the right answer. 911 gigawatt hours. Great. As we wanted. Oh, that's not how you spell. That's not how you write an 11. Gigawatt hours. That's how you write it. Yeah. Oh, capital W. Oh, I did capital W. Great. So that's the answer. Add it up because net change theorem is another way of rephrasing what we concluded in 1.1, that the total change of something is just the area under the curve of its derivative, its rate of change, which is given in this formula. So if these are all the heights and it's a piecewise constant function, then the area is just the width, which the width of all of these is just 1, times the height, which is that rate of change, which is given in the second column. All right, 247 to finish off this video. Let's see what kind of problem I chose for you in this one. The graph below plots a cubic function. And this cubic function, it plots it against the data in the preceding table. This table, okay, which shows the relationship between what year is it and the population of breeding pairs of bald eagles, which has been going up in the continental United States. Great. So it has that data written as points. And it's choosing t equals 0 to be 1963, that first year of data that we had. Estimate the average number of bald eagles per year present for those 37 years by computing the average value of this function over the interval. Okay, so again, nothing fantastically new. They have the data. They modeled the data with a cubic function using some sort of regression formula. We've talked a tiny little bit about that. There's a lot of cool ways of doing that, and a lot of the ways come from calculus. Many of them minimize the squares of the regression, although I think there may be better ways now or more commonly used ways. But yeah, all we need is the average value of this function and we're done. So remember what average value is. So the average value of function p is going to be the integral from 0 to 37 of its value. And now there's no rate of change. Wait, what is this? Is the bald eagle populations. And the previous one, it models it with a quadratic. I just want to make sure what I'm saying is true. Yeah, so there's no rate of change here at all. Just finding an average value, right? Yeah, this is not a rate of change. Again, kind of a weird problem to see. It really is. This section should just be named like applications of the previous 3 sections, because it's really not anything new. It's just application versions of older stuff that we've seen. So again, we're not using, I think, anything particularly new in this problem. Just integrating it. So the function is 0.07 t cubed plus 2.42 t squared minus 25.63 t plus 521.23 dt. And yeah, just use the power rule, plug things in, get to your answer. I'm not going to do this all by hand right now, but you definitely could. And that should be what our answer is. So let's check. So if we look at the integral from 0 to 37 of what we just wrote down, plus 2.42 t squared minus 25.63 plus 521.23 that's, sorry, the average value is that divided by the width of the interval. So divide that by 37. And you're going to get that on average in this time span, there were about 2,038 bald eagles. Average. Between, what are the years that we're looking at? Between 1963 and 2000. And hopefully this should make sense. Do we think that on average there's 2,000 looking at this data? Sure, 2,000 seems believable. Graphically, 2,000's right here. If I draw, hold on, there's a way for me to kind of do this for you. If I draw a horizontal line, wait, was it actually 2,000? Yeah, close to 2,000. If I draw a horizontal line, remember one of the ways that we think of average value is the area above about equal on our interval to the area below. Is that first red area about equal to the second red area? Sure, looks believable. Looks roughly the same. So there we go. That's our answer. That's how many, on average, bald eagles were in the interval. And of course, at the beginning there were fewer, and later on there were more. But that's what's happening, and that's the calculus. And that is the problem. So let me know if you have any questions. Best of luck, and have a good one.